Good morning, everyone. It's a privilege to be standing in front of you today as one of the Talented 12 for 2016. So I'd just like to say a quick thank you to the selectors for giving me this honor. My research began in 2010, well, my journey into my research began in 2010 when I began my Bachelor of Engineering degree at the University of Auckland in New Zealand, my hometown. So I did a degree in chemical and materials engineering, and when I started approaching the end of my degree in 2012, I put a lot of thought into what I wanted to do after I finished. As I'm sure everyone knows, when you get to the end of your degree, that's the process you go into. And I decided that postgraduate research was where I really wanted to go. So in 2013, I moved over the other side of the world, literally the opposite side of the world from my hometown. I moved to Cambridge in the UK, where I began a PhD under the supervision of Professor Steve Lay at the University of Cambridge. My research really sits at the intersection of three separate areas, and that, in a nutshell, is trying to bridge chemical engineering principles with computer science and using that in an application to see how we can improve synthetic work in the lab. So what came out of that was a cloud-based system that enables chemists to remotely monitor, control, and automate their chemical reactions no matter where they are in the world. So in terms of the workflow for synthetic chemistry, I want to highlight it with just an example from the group that was published just before I came over and joined it. So in 2013, the group published a paper on tamoxifen using standard lab equipment to generate 20,000 doses per day of this anti-cancer drug. So when a route is developed to a drug, as I'm sure you all know, there's a large time that is taken by chemists to try and optimize each step of that route to get the best possible result at the end. So my work fits in directly into that optimization process and the actual carrying out of wet bench chemistry work to try and take the time burden off chemists, to make things a little bit more efficient, to see if they can speed that process up so that they can spend their time better on, say, more intellectual pursuits. Why a cloud-based system? Well, there's a number of benefits to cloud-based systems. Your data is available anywhere you are. You don't need to have specialist software to run to access your data or view it. You can usually access it through a web browser. And chemists are already very familiar with using cloud-based software in their day-to-day work. For example, SciFinder and Reaxys. I don't need to go into a huge amount of detail about what those are. I'm sure you're all familiar with it. They're used by millions of chemists around the world to help them carry out their work. Same with the Web of Science. It's a great tool that chemists can use to find literature relevant to their areas. On the more administration side of things, Mendeley, a bibliographic tool used by millions of chemists to keep track of citations, data, that they can then incorporate that into their papers when they're preparing them for publication. And one that I'm familiar with is the founder of ChemInventory, is used by thousands of chemists all around the world to manage the chemical stock in their lab. The research that I'm involved with for this cloud-based control system, though, takes that to the next level. It's not just looking at how we can incorporate it into more the administration side of things. It's more, how can we use that to carry out our reactions, to take the time burden off us, to try and make things a little bit more efficient and a bit faster. So the software is called LayLab. It sits on a server somewhere in the world. It doesn't matter where it is, because it can connect to equipment anywhere else in the world. And it communicates with our lab equipment via the internet. So we can connect to pumps, we can connect to reactor systems, we can connect to detectors such as mass spec, IR, NMR machines, and we can save all that data back into a central database. So every piece of equipment that's connected to the lab, a snapshot is taken of that every second and saved, which means that the user, when they're accessing the system through their internet browser, gets a nice live view of what's happening in the lab no matter where they are. So this is what it looks like in practice. You can access it at any device. I'll pull out my phone here and show you. So right now, I'm connected live to a lab 3,500 miles away and can see what's going on with some of my equipment. I can issue commands to the lab. I can change set point parameters. I can change temperatures and things like that. But one of the major advantages of this, from my perspective, is improved lab safety. So when you're setting up an experiment, you can give accessible and so you can give allowable limits for parameters. So for example, you can say, I don't want my temperature to go above X degrees Celsius. And if that happens, if that temperature is exceeded, potentially indicating that a thermal runaway is about to happen or some sort of major safety issue is starting, the control system will get in touch with you no matter where you are, by text message, by email, by any form of communication, and it will alert you that something's gone wrong. You can then open up your the web browser, access the system, and try and change things to make things, to try and bring things back under control. If it hasn't heard back from you within a set period of time frame, for example, if it tries to contact you at 3 in the morning, it will follow a predefined shutdown sequence to safely stop whatever's happening in an attempt to prevent something going wrong more seriously in the lab. But there are a number of other advantages to the system. First of all, it's great in terms of an audit trail. It records everything that goes on. You can go back and look at reactions in the past to see what happened, how detector output changed based on certain variables changing. For example, how does temperature affect your IR response coming out of your reactor? So you can see how these variables change the process that are happening during your reactions. You can also automate lab procedures. So during an optimization, a chemist would put together a table of reactions that they wanted to carry out to try and optimize the reaction that's actually happening. And what you can do with this system is basically give it the table and it will carry out those reactions for you, saving all the analytical data so that you can actually go back and look at that response and get optimal conditions out of that. But one of the most exciting areas, I think, that the application for this process is in self-optimization of reactions. The system has control over all equipment parameters. You can change residence times or reaction times. You can change stoichiometries by changing rates of addition or the amount added. And you can also get feedback from detectors or analytical gear downstream to see how that has affected your reaction. So the system is able to change parameters and then determine how well the reaction is done based on those changed parameters. So it can start a feedback loop to start choosing new conditions to better the reaction results. And we demonstrated this using an apple reaction using 5 separate parameters. So the system optimized 5 independent variables at the same time. And over 10 hours, it optimized the reaction from unoptimized conditions up to 92% yield, which might not seem like a lot, but it wasn't optimizing just for yield. When a chemist approaches a problem, they don't just look at yield, because you could throw 10,000 equivalents of an expensive catalyst into your reaction pot and get a fantastic result. But you're consuming a lot of that catalyst, and it's very expensive for the lab. So the chemist also looks at material cost and consumption, and also how much material you're processing per unit time. You could do it on a nanomolar scale and get a great result, but then you've got no material at the end to use in next steps in your synthesis process. So we've got the control system thinking and approaching the problem like a chemist would, which is shown by this evaluation function down here. More details about what each of the terms in that equation means given in the publication, so I'd refer you to that. But what we've done is it took into account conversion, because of course we want to incorporate to get the best result that we can, but also consumption and throughput. So it started thinking the same way that a chemist would when they're approaching a problem. We've also given the machine and the control system sight. So we've got a machine vision system set up using open source technologies that can monitor color changes, that can monitor, in this case, the position of plastic floats sitting in reservoirs, so the control system knows how much material is left in flask, so it can switch over if need be. We've also got it set up to run continuous liquid-liquid extraction systems to try and reduce the time burden on chemists for workup procedures. The stuff that I've been talking about has mainly been related to flow chemistry, which is one of the big pillars of Steve Lay's research in the group. But we wanted to try and make it as broad as possible to apply in as wide a range as possible, because most of the time chemistry work is done in batch. So it's very familiar to all of you in glass flasks. So we designed some new glassware that we could slot onto our machines, which has now given us the same level of control over what we had with our flow chemistry equipment, now in batch. So this is a paper we're preparing at the moment, so hopefully it'll be coming out fairly soon. But we were able to automate a process where we had a few batch reactions integrated with flow reactions and then continuous workup before flowing back into another batch reaction. That whole process of multiple steps was completely automated, and all that data has been saved and was able to be managed just by me. I basically started the experiment in the morning, left it running, and then in that evening everything had been finished and I could collect my product out at the end. So I think the future in terms of the applications of this area will really be trying to make a full and free integration between any form of approach to chemical synthesis. So you'll have batch and flow integrated fully together. You don't have to choose between a whole process either in batch or a whole process either in flow. It'll be about what selection of techniques and tools will give the best results to the chemist. So they might say, well, my first reaction might perform better in batch. So I'll choose batch, but then the second reaction performs better in flow, so I'll use that. And you can completely interchange them, so it gives you a lot of flexibility in the lab. I also think that having this sort of data recording system tied in with an electronic lab notebook in the cloud opens up a huge realm of possibilities in the sense of machine learning and neural networking, to use it as training sets to identify data points of interest and to harness the power of the cloud, which is decentralized processing power, to analyze all that data to try and find new things and potentially discover new reactions. So I just wanted to finish off by thanking a few people. Of course, this sort of work isn't possible just with one person. But in particular, I'd like to thank Professor Steve Lay, my supervisor, for his guidance and support during my PhD, and the Wolfisher Trust in New Zealand, which is who have been providing me with full financial support during the course of my PhD. Thank you.